but not in Cairo apparently. Except the one you put there. I guess the assumption is there isn't, but I don't know if that's true.
You should check for two.
Yeah. This is why you never get anything done once you start reading Wikipedia, because you just like can go on forever. All right, so some variations on linked lists. So there's a doubly linked list. And a doubly linked list, each node has a pair of pointers. And the general node structure looks like this. There's data, there's next, and then there's previous. The order of those could be anything. And so we'll stick with a Sentinel for now. So some value in the Sentinel, and then 10, 20, some data values. So the next piece looks like a regular linked list. It points to the next node in the list. And the last element has an entry of null. And the previous part just points back to the previous node in the list. And with a Sentinel node, you could have this point to the Sentinel, or you could put a null right in here. I'm going to have it point back to the Sentinel. You probably wouldn't use a Sentinel in a doubly linked list. We're going to get rid of the Sentinel in a little bit. But this is the idea. If you have a pair of pointers, one pointing forward, one pointing back, what's the advantage of that?
You can start anywhere.
You can start anywhere. Is that what you're going to say? Okay. Yeah, so if I happen to be looking at this 20 node, so let's say you're doing a search. You search for a 20 and you get down here, there's your node. The next time you search, if you have reason to believe that your next search might be for something close to the previous search, it might help you to start at this node and say, should I move left or right? If I'm searching for 10, I could say 10 smaller, let's start searching to the left. So if you have a locality of data in your searches, so picture a million things stored in memory in a linked list, but you're searching for things that are close to each other most of the time, this would be a big speed up. Because a million things in a regular linked list, you start at the Sentinel and you move forward. And if most of the things that you're looking for are close to, the 2/3 point of your list, you got to go through 2/3 of your list every time you're searching. If you can retain where the location of the thing was that you found last time, you might be really close to what you're looking for this time. And it turns out usually there's a lot of locality of data in programs and processes that we create. It's just kind of how it works. And I don't know if there's a solid reason why that is. But it's one of the principles that makes things like cache memory work well. Because we assume that when you access some location in memory, you're probably going to access locations that are near that also. For example, in a C program, you define 15 variables. They're stored near each other in memory. And you're probably going to use all of those variables, or most of them, in this piece of code. And you're not going to use that local variable that you declared 5 routines back, right? So you've got this locality. So that's one advantage. What's another advantage of having these two-way pointers? Yeah, because
you don't need a previous and the current. You just need current.
Yeah, you don't need this double pointer thing that we keep doing where we're keeping the previous and the current. If we want to delete a 20, is that 20 no? Is that 20 no? Is that 20 yes? So we want to delete this. We have to modify the pointers on the previous node. We can find that previous node very easily. Just follow the previous pointer. So let's just simplify our housekeeping as we're looking through this list in cases where we need to do something with the previous node. And of course we still have access to the next node. But the actual operations can be a little more cumbersome. So for example, if we want to delete the 20, let's say that this is temp. And I want to delete that node from the linked list. Well, I got to do a few things. So what do I have to change pointer-wise? Okay, so I've got to change this green pointer. It's still green. I got to change this green pointer, and where should that point? Over here, right? So how do I code that up?
So just previous next equals temp.
I don't have a previous, I've only got temp.
Temp previous equals
There you go.
temp next.
Temp previous, which is this node, and we want to change the next piece of that, right? This thing here, so that's temp previous next is equal to this thing, which is temp next. And that may be horrifying for a few moments, but eventually you can read this as easily as you can read pictures with arrows.
This
Right?
is the same as like in PA1 where we've done something like, if we were thinking about the previous node's next node, you do LL bracket, LL next,
Yeah.
next or something.
Yep, LL bracket previous, close bracket dot
Except that's not hell.
next
So,
bracket dot previous.
I did that and then I realized, oh wait, that's just next.
Yeah. Right, and we can use other variables to make our life a little easier. I mean, we could say, you know, previous node equals temp previous, and then we could say previous node next equals, right? And this is the same as temp arrow previous is p node arrow next, right? It's the same thing. But feel free to do it in pieces, right? Until this starts to feel better. Make yourself a previous. It's just that we don't have to track it as we move through. We can just make a struct node pointer previous or previous node, set it equal to what this is pointing to, and then set its next field. All right, so that takes care of this green node, but we also need to change one other pointer.
Next previous.
Temp next previous
Previous is the next of the temp.
is equal to, it's just going to be temp previous. So temp next is this, previous is this field down here. Set it equal to what temp previous is. That breaks this and has it point back here.
It starts to look like chain link.
Yeah,
And then free town.
and this is what your memory ends up looking like, right? It's just stuff going all over the place, especially after a bunch of inserts and deletes. But this is why GDB will help, right? Because you can take all of that and you can turn it into a picture and then clean it up if necessary. All right, so these statements are a little wonkier looking, but right, still basically the same idea. We're just adjusting pointers to skip over the node that we're deleting in this case.
I feel like that actually, as complicated as, or not complicated, but as many arrows as there is there,
Mm-hmm.
I feel like that actually reduces the amount of lines you're
Yes, it does.
getting, 'cause it's easier to write another arrow than another line.
Yeah, definitely.
That cuts your delete function down.
Mm-hmm. And it absolutely is easier than doing star temp dot next with a star in front and the dot previous and all the parentheses and stuff. Right. And eventually, like I say, this is temp arrow next just means the next thing, and arrow previous just means the previous thing. That connection. gets made.
Are we not supposed to use this for PA2?
I wouldn't use this for PA2 mainly because it's going to really complicate things. The Sentinel node is a little weird because if I follow the previous from here, I'm not going to see null. I'm going to see the address of the Sentinel, and there's nothing that screams out this is the Sentinel node. So if I was searching, I might accidentally think that I've got a 0, right? Unless I put in an edge case which says make sure that this thing's previous is not null. And it's just kind of weird. And yeah, I'd rather you do a singular for PA2.
So if you did a doubly linked list and you didn't put in a Sentinel node, would the last entry's next be null and the first entry's previous be null?
Exactly, yeah. And then it's totally clear that there's nothing before this, there's nothing after this.
So 2 elephants and 2 cities.
Yes.
Well, then how do you refer to the list if you don't have?
Oh, we're gonna do that.
You know for sure it's gonna be there.
So let's do that right now. Let's get rid of the Sentinel.
Did you make up the term doubly linked list?
No.
Okay.
No, that's what it's officially called. Okay, so what if there's no Sentinel? So let's start with the edge cases. So a list with one node looks like this. We're back to singly linked lists. List with one node looks like this. It's got some data and it's got null. 2 nodes. So these are data nodes we're talking about. There's a 100 as our first number, points to a second node. There's a 200 as our second number, and a null. An empty list looks like that. There's no nodes anywhere in sight. All right, so suppose we have a linked list, just called list. So it's a pointer to a struct node. In the case of one node, list would just be the address of that node. In the case of 2 nodes, list would still be the address of that node. In the case of no nodes, what is list equal to? It's got to be equal to something that can't be confused with the address of a struct node. So we give it a special value like null. And we know that null is never the address of a struct node because you can't store anything at location 0, which is null. So we would use null as a flag to say there are no nodes in the list. So an empty list has the case where list is equal to null. Okay, well let's think about our add routine. And it's prototyped like this. We pass a struct node pointer, which is the list, and we pass an integer, which is the integer we want to add to the list. And if list is pointing right here to a node, and we call add, it'll go ahead, it'll change this pointer to point to a new node, it'll malloc space for that, and so on, and everything's fine. But what happens the first time that we try to add something to an empty list? We're calling add of null, comma, 100. It's going to create inside the add routine a new node. It's going to set the data value to 100. It's going to set the next value to null. How are we as the main program going to get our hands on that node? Because it can't modify null to be the address of that first node. It's still passed by value though, right? So main is basically saying call add, first argument is null, second argument is 100. Right, but I'm not actually calling null, I'm calling list. But add cannot change the value of list. List is passed by value. List is equal to 0 when I call add. When I come back, list is still going to be equal to 0. You can't change the value of a variable. If that variable happens to point somewhere, you can change the thing that it's being pointed to, but we can't change list. So when we come back, list is still going to be null. And I've created a node, but I don't have a way to get my hands on it anymore. It still looks like I have an empty list. So we need to do something like have add return a value, which is a struct node star. And now every time we call add, it's going to look something like list equals add list comma value we want to add. And now if we create a new node, we can return that as the function value, and list will get set equal to that first node's address. Now the same thing is going to happen with delete. We're going to call delete, we're going to pass it a list containing a node, we're going to say delete 100. Somehow after I make this call, list has got to be changed to null. Right? And if I just pass list here and it's the location of this node, it's still going to be the location of that node. So again, I need to have some kind of return value, and I could say list equals delete list comma value to delete. That's not totally horrifying, but it's a little unfortunate, right? Because we really want this function to say add this thing to the list. And now we've got to actually make sure that we take the list that we're passing to it and we change its value based on the return value. And it's just kind of it's a little extra step that doesn't really, it's not what you would think of doing first off. We have to do it because of this whole pass by value thing. So that's one thing that happens if there's no Sentinel. We got to have a way to change the value of the list. Our pictures also get weird, right? Because we've always got these empty spaces that we claim is a list, but you know, it's like saying I have 0 purple cows right here, and you can't really like deny that, but yeah. Did I close my presenter or what? Or did it crash? Uh-oh. Yeah, this is a nice infinity mirror, whether you want it or not. It's like, wow.
Oh, that's trippy.
Yeah, I thought it was a glitch at first, but it makes sense.
It is taking a picture of your desktop, and that is on your desktop.
Mm-hmm.
Therefore, it's recording the desktop recording.
Yep. That's a really interesting question. I don't know.
Maybe it gets to the point where the pixels can't be interpreted as anything anymore.
But it's got to know that, so it stops.
But I don't.
Maybe not.
Otherwise, like, render it forever, and you're gonna.
Yeah.
I think it's just taking the image based on the pixels.
You should be able to have a software stop at some point.
Yeah, so it's got to be scaling it, right, by design. So it multiplies everything by some scaling factor. And you would stop when that, like, got here's the other thing. Okay, so here's the list that we pass into this. So this is delete, struct node, star list and integer number. And we do our usual thing where previous equals list, current equals list next. If current data equals num, delete current. But the way we've been doing this, we're never checking this first node's data value. Right? We're checking current arrow data while current starts off as the second node. So that's not going to work. So we could do something like if previous equal num prior. So if we do need like this. So that if current is here and previous is here, we can take previous next and set it equal to current next to skip over the 300. But we're missing the possibility of deleting the first node, so we have an edge case now. We have to, before we do any of this, see if previous data is equal to the number we want to delete. And if not, then we can check the current node's data and we can start looping on that and moving our pointers down the list. So suppose we are deleting 100. Suppose this is the node we want to delete. Well, there's no node before it that we have to adjust to skip over the 100 because the 100 is the first part of the list, the first node in the list. So all we need to do is somehow change list to point to the 200. But we can't change list from inside this function. I mean, we can change this variable list, but when this function is called from main, and inside main we say delete ll comma 100, the value of ll after this call is going to be the same as it was before, because everything's passed by value. So in here I might say something like list equals list arrow next, which changes list to point to this. So now inside the mind of the delete function, my linked list begins with 200. And I could free previous to get rid of this. But when I return, ll is still pointing to this 100, which has been freed now, by the way. So as soon as I try to do anything else with ll, I'm probably going to seg fault. So again, I need to return a pointer to a struct node and do something like ll equals delete ll. And I have to check for this edge case before I start looping. And there's all kinds of just sort of extra edge cases that come up where you find yourself doing one of two things instead of just one thing. You have to check to see if you're dealing with the first node, if you're inserting before the first node, if you're deleting the first node. And if you are, you do one set of things that usually returns a new list pointer. And if you're not, then you go ahead and you do the things like what we do with a Sentinel. So you can do this, you can live without a Sentinel, it just simplifies the code. And for PA2 in particular and PA1, I don't want to get into those edge cases more than we have to. So we're working with a Sentinel. But later on, as I've said, when we start working with trees, we're not going to have Sentinel nodes. And we will have to deal with things like returning a pointer to a struct node so that we can change what the original struct node is. But we'll get there in a few weeks. All right, questions on that? So Sentinels are good. So circular linked lists. This is another variety. The only difference with a circular linked list is when you get to the last node, instead of being null, you just point back to the beginning. And again, without a sentinel, you'd go back to the first node. With a sentinel, you might go to the first node, you might go to the thing it points to. It depends. So I won't worry about the sentinel, I'll just go back to the first node. Now this is useful if you don't want to worry about the edge case of running off the end. For example, when you're doing a search, you can come through, and if you don't find your number, you'll eventually get back to the beginning, and you can somehow detect that. Maybe if the numbers are in increasing order, you'd know that the number you've just found is smaller than the previous one, and that would tell you. But it's just kind of a convenience, but it's also useful, again, if you want to start at some location and periodically move down the list. Right, so I might start at this location and take some action. And I remember this location so that the next time I want to take an action, I take the node that this points to, and I do some work there. And then the next time I'm going to take the node that that points to, and so on. And when I get to the end, I'm not really at the end. There's still another node I can point to. Now I can't store a limitless amount of information in this, obviously. But if you're trying to pull things off from successive nodes and something else is taking care of making sure that you're not running out of memory, right, a circular structure will help you. And when we talk about queues in particular, which is coming up next, circular lists can help with implementing a queue. And we'll see why. But the algorithms are pretty much the same as long as you don't accidentally get stuck in an infinite loop. Now, if you're searching for a number and it's not in there and you just keep following links, you're going to follow your links forever, right? But if you avoid that possibility, it's a convenience. And from the end, you get back to the beginning. When we talk about hashes, we'll see some of this also. So it's kind of like an array with no end to it. The end just wraps back around to the beginning.
With a circular list, if you had a good search function, you could take care of a lot of edge cases.
Mm-hmm. Yep. And with this, even without a Sentinel node, there's no edge cases for inserting, because there is no first node in the list, right? Well, you still have the case of an empty list, but inserting before here is really inserting something between this node and this node. So you take this node and have it point to your new node and have the new node point where this was pointing, which was this node. And so now your new node, this points to your new node, and your new node points where this was pointing, which is up here, and it was just sandwiched this in between what was the first node and the last node.
And when you delete a node that you're using to reference to the list, your name, you just have the new reference be the next node in the list, and there'll always be one as long as there's a list.
Right. As long as it's not empty, you can delete the first one and still point to another node in the list. So sometimes circular linked lists are handy. So as we go through this course and as we go through 223 in spring, we're going to bump into all kinds of data structures. Okay, we've seen linked lists, and we're seeing a few varieties on the linked lists. We're going to do stacks and queues next week. We're going to do trees, and there's a whole variety of trees that we'll talk about. There's tries, which are trees with lots of branches on them. And there's hashes, which are very efficient ways to search. And there's heaps, which are efficient ways to implement queues. And we're going to get this whole collection of data structures. And the more you understand these different data structures, the more you can sort of pick and choose from what makes up each of these things to build the data structures you need for whatever it is you're doing. Sometimes you just need a linked list, right? And if you're working in Java, linked lists are built in. There's a library or a yeah, library of objects that implement linked lists and work with them. But chances are you're not going to need just a plain old linked list. You might need a linked list where there's 5 fields, and one of those fields is an integer, and one of them is a string, and one of them is another linked list, and one of them is a tree, and one of them is a stack, right? And you're not going to find a library pre-made of that data structure, but it might be what you need for your particular problem you're solving, and you can cobble it together. So understanding these things is important, but down the road we'll be using these things from libraries. We won't have to actually build a linked list unless we want to. But you got to understand how they work to be able to use them, basically. Okay, so it's the same problem you have with calculus. You could just learn the rules for taking derivatives of polynomials, move the exponent over here, subtract 1, right? But if you don't understand what's going on with that, you can't do differential equations, for example, where you actually use derivatives and equations. You got to understand what's going on. And then once you've understood that, you can use these rules to, here's how we take a derivative. Right? So this is not just a hazing kind of thing. Right? It'll help with everything you do in computer science. And data structures is one of the 3 keys to computer science, in my mind at least. And increasingly when you're writing a program, one of the first things you're going to do is figure out your data structures. And then you start writing code around that. But that's sort of the backbone on which programs are written more often than not. All right, yes?
So that's one of the 3 keys, what are the other 2?
So this is just my personal opinion. 3 keys to excellent programming. Grasp of data structures, debugging skills, and rapid prototyping. Being able to put together a version of what you're trying to do very quickly and start modulating around that. That's not a scientific list. It's just kind of, if someone asked me what do I think are the 3 top things, that's sort of what I came up with. So, and you get chances for all of those in here, right? So definitely a lot of debugging opportunities, especially with this stuff. And rapid prototyping is things like, you know, I want to build a list so I can check my print routine. So write some statements to do mallocs and set some data values and set up some pointers and bang out a print routine. Don't worry about error checking, don't worry about formatting, right? Just get it together and start working with it. So let me tell you what your Friday ODP will be, in case we don't see each other on Friday. So I'm going to ask you to create a linked list of struct nodes by hand containing a Sentinel and 3 data values. Right, so I'll ask you to make a linked list that looks like this. And I'll probably pass you the 3 values I want in the nodes. So I'll pass you X, Y, and Z. This should have an X, this should have Y, this should have Z. The pointer should be set up, this should be null, and I don't care what the Sentinel's data value is. And this no ordering here. X could be bigger than Y, and Y could be smaller than Z or anything like that, right? It's going to be really just sort of most straightforward possible interpretation. Take 3 integers X, Y, Z, build 4 nodes, a Sentinel, 3 data nodes containing X, Y, Z, set up the pointers. And it's just doing the 4 mallocs and some assignment statements. Data equals X, data equals Y, data equals Z in the arrows. Okay, so a slightly more elaborate version of ODP 407 where we just had 2 nodes and we set up 1 pointer. Same thing. But just to make absolutely sure that by the weekend everybody's comfortable with mallocs and arrow data, arrow next, that kind of stuff. So that should be pretty quick to do. So that'll be 208. Other questions? Yeah.
Is there a way to realistically test if your program is freeing correctly?
Yes. Did we do this?
We did,
I forgot what.
Let's do this again then. Yeah, so your command is valgrind.
Oh, right, okay.
You remember that?
Yeah.
Okay, so valgrind space name of the executable, and when your program exits, it gives you a report that says if you had memory leaks, basically. All right, I got a few minutes. Let me start you on what's going to come next week, just for you to kind of think about it. We're going to talk about two new data structures, stacks and queues. And let me give you a model to keep in mind for each of these, just to sort of let it be there. So what's a stack? So here's the way I learned stacks. You go into a Chinese restaurant, and it's a buffet, okay? So you walk up, and what's the first thing that you do? You get a plate, right? And there's this machine, it's spring-loaded, it's got a whole stack of plates. And it's weighted so that when you take a plate off the top, it all moves up and there's another plate there. Okay, so in an ideal setting, you can only take the plate off the top. Of course, if that one's like wet, you take the one below it, but you only take a plate off the top, okay? And if you wanted, you could put the plate back on the top. You can't take the plate that's halfway down the stack, okay? And you can't put a plate into that place that's halfway down the stack. If you take too many plates, the stack is empty, and the next person tries to take a plate, there's nothing there. Okay, the dishwasher comes out, and they've got a whole bunch of plates, and they put those into the stack, and they usually do it all at once. But if you didn't do it all at once, you put one plate on top, and then another, and things would keep moving down. Okay, if you try to put too many plates on there, the spring's compressed all the way, you can't put any more, and the plates fall off. Okay, so that's called a stack overflow. Right, that's the website. If you try to take off a plate but there's no plate there, that's a stack underflow. It's a less common situation. When you say what?
Is there a site called stack underflow?
I don't think so, because it's a little underwhelming. When you put a plate on top, that's called pushing onto the stack. When you take a plate off, that's pulling from the stack. And there's one more thing I was going to say. Oh, so somebody comes out and they put plates back on there, right? The next plate that comes off the stack is going to be the last plate that was put on the stack. So you put a plate, put a plate, put a plate, put a plate. That last one that you put on, that's the first one that someone's going to take. Okay, so we use the word LIFO, last in, first out. The last plate that went on there is the first one that comes off. Okay, so stacks are going to follow that model exactly. We'll talk about overflow, underflow, full, empty, pushing, popping, last in, first out. Okay, but you can kind of keep that model in your head. The alternative to a stack is a queue, and the model for a queue is a checkout line at the store. So there's a bunch of people standing there. One person's being helped, 5 people are in line. If you come into line, you're not going to be the next person waited on. You're going to be the last person waited on. Everybody who's already in that queue is going to get service before you. But if somebody comes behind you, you're going to get service before they do. So it's first in, first out. The first person in line is the first person out of line. The second person in line is the second person out of line.
Exactly how support works.
Yeah. So that's first in, first out. A stack is last in, first out. So it'll be kind of duals to each other. So we'll spell that out on Monday, and we'll start looking at these in details, and we'll look at some algorithms for them and so on and so forth after whatever questions come up and whatever you want to talk about. Sound good?
They're kind of opposites, aren't they?
Yeah, in a lot of ways they are. And when you code them up, you kind of see that come out.